All right, let's go ahead and get started. I think we have probably enough people here. So, okay, so I've put up some problems on the board, which you can do if you want or not. Kind of up to you. I'm not going to make you. But these are just some ways of kind of refreshing yourself with Big O, or if you don't know any Big O, then you probably want to start with reading a bit about that. But okay, so I'm here to talk about, obviously, how to do well in coding interviews. So my background is as a software engineer. I was at Google for a while, a bit at Microsoft and Apple as well. Was on Google's hiring committee, did a lot of interviewing. And then what I started doing is, wrote Cracking the Coding Interview, another book for PMs. And what I do now is a lot of consulting on both sides of the table. So I do what I call acquisition interview coaching, which is basically when startups go through interviews, they get interviewed just like a typical candidate would, each employee does. And so companies bring me in to help prepare their engineers and their PMs and other people for those interviews. And so I'll tell you about a few of the things I've seen being able to prepare people for those interviews. And then I also do the other side and help companies build out their hiring process, which if you're interested, if you have questions on the other side, I'm doing a talk on that at 5. I think back in this, actually the same room. Okay, so without further ado, slides are online. Go to go.gayle.com/codingprep. Or you can shoot me an email with the subject coding prep, gayle@gayle.com, or g@gayle.com, whatever. Anything at gayle.com, actually. It all goes in the same bucket. So with the subject coding prep. And then, now people aren't doing it anyway, but photos are fine. I know that's how people record info on the slides. So go ahead and take pictures to record whatever you want. All right. With that said, I'm going to dive into coding interviews. I'm going to give a little bit of a high-level description, but most of this will be pretty technical. All right, so there's a couple different types of interviews you're going to see. Behavioral interviews is one. Design interviews, so that means system design for a back-end person typically, but it could mean other architecture design questions. And then CS fundamentals, coding, algorithm, whiteboard interviews. They have a lot of different names, all kind of referring to the same thing. And what I'm going to talk about today, because I only have an hour, is just pretty much just the last section. But when you see the slides online, as you go to the very bottom, I have some extra bonus slides that I'm not going to talk about today that have some of that content on there. Okay, so a CS fundamentals interview, if it's an hour long, it's something kind of like this usually. So about 5 minutes in the beginning about behavioral questions. Then the rest of it is on technical questions. Many interviewers try to go to 2 questions, but that's very subject to the interviewer and the company. It's not as subject to your performance. Sometimes people will think like, oh, I only got to 1 question, so that's a bad sign. Like, if you interview with me, I pretty much only ask 1 question. So you're not really ever, if I'm the interviewer, going to get to a second question. Because I just ask 1 question, and I have it be a pretty hard one that kind of gets harder and scales up. So don't see that as a reflection of your performance, because it's really not. And then usually there's a bit of time at the end to ask questions to your interviewer about the company. And that's something you want to prepare for all of these sections. Today I'm just going to talk about the coding stuff, but you want to prepare for all of them. So algorithm interviews, what interviewers are looking for typically is analytical skills, problem-solving skills, whatever you want to call it. It's more or less intelligence tests. Companies don't want to put it that way, but that's really what this is about. And then there's things around how do you think about problems? Can you break things down? How do you think about trade-offs, communication skills? There's another thing I really like to see in candidates, which is a willingness to push past hard obstacles and push through hard problems. There's some people I interview who are what I call like mentally lazy, which doesn't mean necessarily that they're not smart. They might be smart, but they're just lazy. They don't really want to think about problems. And so as soon as something gets hard, they're like, well, I don't know, I'd look it up. And that worries me, because there are not always answers online. Yes, my questions you can probably Google and find answers to, but a lot of stuff we do, there aren't answers online, and I want to hire people who have a powerful brain and they can figure this stuff out on their own. And then a strong foundation in computer science is often something people are looking for. That doesn't mean necessarily having a CS degree. It just means there's a fundamental basis of data structures and algorithms that interviewers often look to see that you're very comfortable in that. And frankly, it's not actually that much stuff to learn. You can learn in a pretty short amount of time. You want to learn it really, really well, but you don't have to know a lot of crazy advanced topics. With the CS degree, it's nice to have. It'll help because by having a CS degree, you've learned what a binary search tree is and a graph and a lot of this stuff, but it doesn't, what matters is knowing that stuff, not having a degree, and it's really not that much stuff to learn. I had a friend who was interviewing a few years ago for a job at Facebook, and when I started prepping him, I was like, okay, well, I mean, you know what a hash table is and this kind of stuff, and he's like, what? I'm like, you don't know what a hash table is? Okay, we have a long journey ahead of us. But a couple weeks later, he interviewed and got an offer, and he's doing very, very well there, and still has not given me my commission. But fundamentally, no, he did not know a lot of stuff. He was truly, truly self-taught. He's so self-taught, he actually has a music degree from a for-profit university. And he didn't learn computer science, ever. But fundamentally, he's a smart guy. And he was able to figure out how to solve problems. He had to learn this stuff, yes, but he figured out how to do it, and he did very well. The biggest thing that hurts people who don't have CS degrees is essentially insecurity, imposter syndrome, whatever you want to call it. It's the feeling when they get a question, the interviewer says, how would you write given a binary search tree, design the algorithm to do such and such, and they go to they fall back to this mode of, well, I don't do binary search trees in the real, I haven't done this, I don't know how to, I don't have a lot of comfort with binary search trees. They know what a binary search tree is, they know how to implement, they know all this stuff, but they get nervous and they basically give up. That is what hurts people who don't have CS degrees. It's not actually lack of knowledge typically. Typically they have the knowledge that they need to have once they put in that little bit of time. So if you don't have a CS degree, don't worry about it. It doesn't matter that much. You just have to learn the stuff and you can learn it. It's not that hard. All right. So this is the stuff that you really, really need to know. You need to know the stuff very well. You'd be very comfortable with it, but you don't need to know really advanced topics beyond this. So a few things I want to specifically mention here. TRIES, T-R-I-E-S, is something I call out because it comes up in a lot of other interview questions, and it's not something that a CS class does actually spend a lot of time on. It's a simple concept, but you want to make sure you're familiar with it. Big O, time and space, is extremely important. That is the way that we talk about efficiency of algorithms, and the point of these questions is, can you design an efficient algorithm? If you don't know that language, you're going to have trouble doing that. So you want to be really, really comfortable with that. And then dynamic programming. When I say that, I don't mean knowing advanced topics and knapsack problem, all this stuff. That's not that important, actually. You need to be comfortable with that concept and solving problems that you haven't seen before using that kind of pattern, but it's not about knowing advanced dynamic programming problems. So for your preparation, what I recommend you do is, first of all, make sure you really, really know Big O. That doesn't mean master's theorem and really advanced stuff. It means you have an algorithm you can compute the Big O time or get pretty close to it. Implement that whole table of data structures and algorithms, implement all of those from scratch. You should be, by the time you walk into the interview, you should be happy if you get a question like that because it's so easy for you to do. If you get a question that's like implement a binary search tree, great. That should be an easy thing to do when you walk into the interview. And I mean just a binary search tree, not balancing, none of that stuff, just implement a binary search tree. That should be easy for you. Most interviewers won't ask you actually to implement a binary search tree, but they might ask you to implement a binary search tree which has this modification to it, and you really want to know the fundamentals well in order to do that. Then practice on real interview questions. There's people who practice with things like, there's various lists on Business Insider or places like that that have top 10 crazy Google interview questions, and they're picking those because those are crazy interview questions. They're not actually what's happening typically. And in fact, most of those lists are actually just flat out lies. If you go back and track their sources, it wasn't even from Google in the first place. So practice on real interview questions. That also means that reading algorithms textbooks, it's so far beyond the knowledge of what you need to know. It's like you want to figure out how to put on a Band-Aid on a kid, and you're learning surgery. It's okay, but that's just not a good use of your time. You'll learn a lot. It's just not a good use of your time for interviews. So practice on real interview questions. If your interviews will be on a whiteboard, practice coding by hand. This is really, really important. Not just because of the sort of psychological effect where coding and being in an environment you've been in before makes you more comfortable, and not just because of that, but because coding by hand actually takes a little bit of a different process. So to make an analogy, If you are driving from here to someplace 2 miles away, and you basically know how to get there, directions would be nice, but if you basically know how to get there, like, you'll be fine. You might take a wrong turn and whatever, but you'll get there sooner or later, and it really won't be that bad that you didn't know exactly where you're going. If you're walking here to someplace 2 miles away, and you're on foot, and you start off walking the wrong direction, you can waste a lot of time, because walking is slow. And it's the same thing. Coding by hand is really slow. What you've done is you've gotten into a mindset in coding of, you basically understand what you're about to do more or less, and frankly, it's only like 10, 20 lines of code anyway. You'll just start writing it. And that's fine on a computer. It's not so fine on a whiteboard. That's any time you write a function you didn't need to do or something like that, you waste so much time. So you want to practice coding by hand so that you really learn and embed into your mind the cost of mistakes, because you want to get things right the first time around. If not just because your interviewer will want to see that, and I don't want people to freak out about mistakes. Mistakes are not that big of a deal, but because when you start writing stuff you don't need to do, you can waste so much time. Handwriting on a whiteboard is really slow. And then do mock interviews if at all possible. There are various mock interview services out there. You can use those. You can also just grab a friend and take turns interviewing each other. In fact, it's actually really useful, especially if you're nervous, to get experience as an interviewer, because it's a lot less scary to be a candidate when you've already been an interviewer and you kind of know what the interviewer is doing and why they're doing certain things. So do mock interviews if at all possible, and push yourself through problems. Too many people think about interview prep as like learning a ton of questions and answers, and it's about getting better at solving problems. If you give up as soon as you get a hard problem, you're not actually improving your skills. The point is to actually get better at solving problems. So really push yourself. Okay, so what's expected in these questions is not to know the answer right away. You're not expected to be so incredibly brilliant that although you didn't know the solution already, you just looked at it and you just knew how to solve it. And you're also not expected to code perfectly. It's fantastic if you do, but that's not really expected. And that's actually, having somebody who has these attributes is actually pretty rare. What I want to see is your thought process, which some aspect of that is how quickly do you move through the problem, but that's not purely about the number of minutes to solve a problem, because I might give one person more help than another. Someone might be struggling a lot and need a lot more help. And so, yes, they took 20 minutes to solve this problem, and you took 30 minutes, but you did it independently, and they did it within 20 minutes with a lot of help. You might well have done better, even though you took longer. So it's not purely number of minutes, but yeah, speed is kind of in there. And ability to solve it independently is kind of in there as well. And then I want to see real code. For them, and this is speaking in general, so there can be individual interviewers with different preferences, but pseudocode is generally not acceptable. And the reason is that pseudocode, one, you're writing real code in the real world, so writing real code shouldn't be a big issue for you. But also, when you allow a candidate to write pseudocode, it's like you haven't set the rules to the game. What is pseudocode? Is pseudocode what you see? Is pseudocode something that looks pretty darn close to real code? Or is it something that's like step 1, search through array, step 2, do this? Or candidates start doing things like saying, oh, I'm going to store this stuff in a list. And they're not thinking about, well, is it a linked list? Is it an array? If it's an array, you have indexing. If it's a linked list, you can't just go to the 7th element in the array or in the linked list. And if it's a linked list, you can append and prepend things, but if it's an array, you can't do those things. And so when you allow pseudocode, it's too vague what people want. So most interviewers just expect real code. That said, the point of interviewing, and if you want to hear a lot more about this, go to my talk at 5, so I'm not going to go into a lot of this here, but the point of it is about signal, not literally what happened. So both of these bits of code are wrong. They will both fail to compile. The first one is incorrect, it has compilation error, because that should be list.add instead of list.insert. Who cares? Right, that's not, sure, the code is broken, but it's not like an interviewer is going to look at that and be like, oh gosh, that is a bad software engineer. They said list.insert instead of list.add. I mean, that's not something a typical interviewer will care a whole lot about. The second one, well, that's a much bigger deal. Assuming this is an actual typo, where they only wrote one, or assuming this is an actual confusion of single equals versus double equals, which I have seen. I've seen people who repeatedly make this error and don't really understand the difference still between assignment and comparison. That is a much bigger problem. Both are compilation errors, but the signal I get from each is very, very different. So when people say you have to have flawless code, and I will push people, I will encourage you, write your code under the mindset of writing flawless code. That does not mean literally interviewers are freaking out over every little error. It very much depends on what that error is and what it actually indicates about you. Many, many, many errors are not big deals at all. So just general advice before I dive into a lot more technical stuff, drive the interview, drive the process. You should be the one looking at how to solve the problem, how to optimize, continue to look for better solutions, going into testing immediately. You want to be the one who is driving through that and not waiting for your interviewer to say, can you optimize this? Can you run through some test cases? You want to be the one driving. Show me your thought process. Try to talk out loud as much as you can. And that's a skill that I would recommend preparing. As awkward as it is, try to talk out loud, even as you're solving it one-on-one. Try to talk out, or not one-on-one, by yourself. Try to talk out loud as you're solving it. Better yet, if you want to make it extra awkward, have someone else in the room with you. Even if they're like someone that's not even paying attention to what you're doing, just having someone else in the room listening to you talk helps you get a little bit more in that mindset. And then pay attention to your interviewer. There are many, many times where interviewers jump in to give hints and candidates dismiss it. So that might be, I start saying, okay, well, here's the value you get if you plug in 1. Here's what you get when you plug in 2. Here's what you get when you plug in 3. And then as soon as I give the control back to the candidate, they ignore everything I just did and go back to what they're doing before. The obvious thing should be, what happens when you plug in 4? Like, let me take over where she left off. Or I ask a candidate, I make a suggestion like, what if you thought about this as a list of the number of people in each country? And they kind of ignore me and go back to what they're doing before. Or I say, I've said 3 times, what will happen when there's duplicates? And they answer that question once, and they do it the second time, they answer it again. And then, third time, they answer it again, but they never start asking this question on their own. Pay attention to the interviewer. Pay attention to the hints they're giving you. When I speak up to make a comment or a question, there's a reason I'm trying to guide you, and you want to make sure you're really taking the value of that guidance. But the people in the back, there's room up here to sit. That might be less awkward than standing, but you guys can stand if you want. Okay. So now let's talk about how to actually develop an algorithm. So I'm going to go through this. You can get this at crackingthecodinginterview.com. Click on resources. This is basically a flow chart for how to move through questions. I really, really, really recommend actually following through with this flow chart. That means actually having it out in front of you, and you solve a problem. When you read a question, you say, okay, go to that first step, listening. Okay, now the second step. Okay, second step is draw an example. There are many times when I do presentations like this and then have the opportunity to actually interview people, and I see people, despite my computer advice, who just skip over to step 3 or 4. Please don't do that. This is like that for a reason. So actually follow this step by step by step. And what today is going to be is basically going through this in more detail. So first step, do this seriously. First step is listen to carefully the problem. So this is the, listen carefully to the problem, make sure you heard it correctly, repeat it back, yes, all that stuff. I'm making a step further than that, though. I'm saying listen for clues in the problem. Interviewers generally don't give unnecessary information. So every single piece of information in the problem, you could, with good reliability, bet you actually need it. So, for example, given 2 arrays that are sorted and distinct, find the number of elements in common. There are many times when people start to solve this, and the first solution is something like, okay, for each element in the first array, look through it in the second array. And that's fine as a brute force. It's slow, but it's fine, totally fine to start with a brute force. And then by the time they try to optimize, they've forgotten about the fact that I said the array was sorted. And now you are out of luck. It is literally impossible to get to an optimal answer for this problem if you forgot that the array is sorted. So pay attention to those specific details in the problem. And what you should actually get into the mindset of doing is think, okay, she said that the array was sorted. There is a way we are going to use the fact that the arrays are sorted. I don't know how it is, but we are going to use that information. The optimal answer will hinge on that piece of information. So if you have an answer that could work just as well as on unsorted arrays, you can bet that it's not optimal, and that somehow you're going to use this sorting piece. So second step is draw an example. This is the step that is possibly the most important and that people skip over the most. It is so, so, so useful. So let's start with the problem we just gave. Given 2 arrays, sorted and distinct, find the number of elements in common. So think for a moment about, if you were up at the whiteboard right now, what you draw as an example of your input. So if you have a picture in your mind, hold that picture. Most people draw something like this, more or less. Different numbers, probably, unless I got very lucky, but basically something like this. It's a valid example, it's just not a very useful one, because it's really small, and it's actually kind of a special case. It's two arrays, they're the same length, which was never in the problem. They only have one element in common, which is kind of a special case. And to make matters worse, that element's even at the same index. This is a better example. It's just much more cumbersome. It's bigger, they're different length arrays, there's multiple elements common, but they're not even at the same index, but one is actually at the same index, but the others are not. That is a much more generic example. Think about it as, if you were to run only one test case through your code, which one do you want it to be? You probably want it to be the second one. Because this first one, there could be errors around the lines of it only actually finds one element, it only works in arrays the same length. Things like this, it walks through them at the same exact time, which means that it would find that element common but not these other ones. So you want your example to be as generic as possible. And this is not an example you will actually use as a test case. This is an example you will use just to generate an algorithm, just to start working through it. Because you'll usually be working mostly with one example. So this is really, really important. So you want your example to be something that you have to work for it. Meaning that when I put this up on the board, as soon as you see this, and I ask you how many elements are in common, 1. You glance at it, you know the answer. Right? This one, if I ask you how many elements are in common, you don't just look and say, oh, well, it's 3. Right? You had to do something to get to that answer. That's work. And you want your example to be cumbersome enough that you had to do work to get to that answer, because that work that you did might very well be an algorithm by itself. So what that means is examples should be large and generic. So it should be one of the keys to making you do work is making it be large, but also be generic. Try to avoid special cases like only one element common or they're the same length, things like that. Third thing is to get a brute force. What I mean by this is just, look, if you have an algorithm in mind, say it. Don't hold back. Don't think that you want to hold off until you have a great algorithm because this first one is stupid and obvious. Because even if it's stupid and obvious to you, there is going to be some portion of candidates, no matter how easy the problem is, for whom it's not obvious. And you do not want to get confused with those. If you have an algorithm, say it. Even something really slow and stupid is better than nothing. Because at least it separates you from those other people. But also because in some cases, it's actually a pretty good algorithm. Sometimes you actually can't do much better and it ends up being a pretty good one. And in many cases, you make optimizations from that. But it's certainly better to have something than nothing. But what I mean by that is just you say, well, one way of doing it, or here's a brute force way of doing this. That'll give us this runtime, and then you immediately go into optimizing. Do not code the brute force. In fact, never code until your interviewer has told you to code. You can ask them, should you want me to code this? But never, ever, ever start coding just because you see an algorithm. I see this all the time. People say, well, you can do it like this, and then they start trying to code it. And I'm an assertive enough interviewer that I'm going to go there and I'm going to tell you to stop. And that's what every interviewer should be doing. But there's a heck of a lot of interviewers out there who honestly don't really know what they're doing. And they will let you code stuff that they never actually wanted to see. And then you just spent 20 minutes doing stuff that was unrelated to the interview, and it ends up totally unfairly hurting you. So never, ever, ever code until your interviewer has explicitly given you a sign-off to code. And also, don't use code as a way of explaining an algorithm. It's a very, very, very time-consuming way to explain it. You can walk through examples if you want to explain it in more detail, but code is not a good way to explain an algorithm. Okay, once you have a brute force, or whatever the first algorithm is that pops into your mind, explain it, talk with the runtime, then optimize. And optimization is where I'm going to spend a good chunk of the rest of the time, because that's where a good chunk of interviews is spent, is on optimizations. So there's a couple different ways I'm going to talk about. One is BUD, the other thing is space and time, and third thing is what I call DIY. So BUD means bottlenecks, unnecessary work, and duplicated work. And these are three things that I find are often things that you can identify in an algorithm and then optimize away. So bottlenecks. So we've talked about this problem a couple times. Two arrays, sorted and distinct, find the elements in common. Okay, brute force algorithm. Walk through this array. Check if it's start with 1, check if it's 1, go to 12, check if it's 12, 15, check if it's 12, 15, 19, check if it's 19. So what's our runtime of that? I already kind of had it up there, but what's the runtime of that? Yeah. So really important to say m times n, AB, not n squared. That is the most common error people make with Big O, is nested loops, n squared. Well, they're different loops, right? And a good way of thinking about this is, okay, you say n squared, what's n? And inevitably people say the size of the array. Which one? It's two arrays, right? So this is a slight tangent on Big O. With Big O, one advice I have is if you said n squared, or even if you didn't, just don't use n ever. Just strike n entirely out of your vocabulary for Big O. Because this is actually the source of the problem, is that you say sorting is n log n. Walking through an array, that's O of n. Getting the max element in an array, that's O of n. Size of a grid is n squared. Well, what you forgot about is that for that problem, you defined n to be this other thing. So sorting is not n log n. Sorting is s log s. So a lot of the problems come down to just using the wrong variable names. So just don't use n anymore. If there's no ambiguity at all, that there's nothing else n could possibly mean for that problem, fine, but basically just stop using n, and that'll solve a lot of your problems. Okay, so brute force algorithm, A times B. So our bottleneck here is this B thing. For every element A, we're doing O of B work. From this, is there 1? Is there 12? Is there 15? Is there 19? So how can we do better? Yeah, so this is sorted. So if we want to check if something's in a sorted array, that's what binary search is for. And in fact, the fact that the interviewer said that these arrays are sorted should make you have at the top of your mind, how are we going to use the fact that it's sorted? Oh, well, it's a lot faster to check if something's in a sorted array. So that gives an A log B algorithm. Well, log B is still kind of our bottleneck. If we still want to optimize, like we could bet that we want to just get rid of that log B. We don't want to be multiplying those things together. So what's an even faster way to check if something is in an array? Hash tables. In fact, when in doubt in interviews, hash tables, seriously. Like, that's a legitimate strategy that's going to be part 2, hash tables. A lot of interview questions come down to hash tables. Have at the top of your mind, constantly think about using them. So yeah, throw B into a hash table, and then for every element A, just look it up in B. That gives A plus B. That's pretty good, and in fact, there's a concept I'm not really going to talk about a lot today, but called best conceivable runtime, which is totally different from like a best case. Best conceivable runtime means like, given the nature of this problem, what is like theoretically the best runtime you could imagine? For this problem, you can't possibly have an algorithm that is better than O of A plus B time because you have to at least look at every single element. So that's going to be our limit in terms of performance. So that's great. We're at our limit of performance. We cannot possibly do better than O of A plus B. But what's really weird here is this hash set solution doesn't use the sorting piece. So what happened here? I said earlier that interviewers probably don't give necessary information, and now we have an optimal time algorithm that doesn't even need to be sorted in the first place. So what happened? Space, yeah. So yes, it's optimal time, but it's not optimal space. So the space is now our bottleneck. We're using O of B space here. So now we want to think about, okay, how can I still get O of A plus B time, but get rid of that bottleneck, which is my space complexity? That means no more hash set. And there are an infinite number of possible runtimes and space complexity, whatever. But you can bet that if you're dropping O of B space, it's probably dropping to O of 1. I mean, it could be log B, but that doesn't happen a whole lot. So we're probably talking about an algorithm that has O of A plus B time and O of 1 space. And what would that look like? Remember that the arrays are sorted. Yeah, walk through them both at the same time. Kind of like what I'll call a sorted merge. It's a similar step as in a sorted merge. So walk through with 2 pointers, comparing the 2 things. So this technique is identify that bottleneck and just really focus on how do I get rid of that bottleneck? How do I get rid of that bottleneck? Did you have a question back there, or did I tackle it? Mm-hmm. so it doesn't even have a larger element. I mean, it depends on the nature of the problem. So for this kind of problem, the elements, the specific values in the array don't matter. Like, I could have these be much, much bigger values, and it wouldn't make a difference in terms of the problem. And actually, but you did remind me of something that I want to be very clear. When I say make a generic example, I still mean concrete. I'll see people who write what they think of as generic examples, and it's like, okay, element A, B, C, dot, 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 dot. Generally speaking, that makes things harder. Make it concrete, specific values, specific numbers. Focus on what matters. Like, the size of the numbers don't really matter, as long as they're not like the same. When you have a lot of problems involving words, the size of the word may or may not matter. If it doesn't affect the problem in any way, the size of the word, keep the words short, make things easier. But do keep your examples concrete. Okay, second part of BUD is the necessary work. So new question, find all solutions to a cubed plus b cubed equals c cubed plus d cubed, where a, b, c, and d are between 1 and n. So what's a stupid way of doing this? Yeah. 4 nested loops, right? Dumbest possible way. It's fine, it's a starting point. Don't actually code this, especially that, because that's not actually real code. But don't actually go and write this code. Yeah, it's fine. And we can make this a little faster by, might as well add in a little break statement here, because once we find one solution, there can't be more values of d that we can plug in. So we can at least add a little break statement in there. Doesn't really change our big O time, but might as well. But that might want to get you thinking about, well, wait a minute, we add a little break. Like, if there's only one value of d that works, do I actually need to loop through to find it, or can I just get to that value? Which, leading question, yeah, right? If I told you find d in this thing, I don't think you would do what your algorithm is doing, which is plug in 1, plug in 2, plug in 3 until you get to the right answer. Right? You'd probably just solve for d. And certainly then the computer can just solve for d here. So just solve for d. Right? And so this is what unnecessary work is. It's these little things where you're like, well, I can just add in a break statement here. Well, I only need to search this half of the array. And these things don't change the big O time. But very often, they are related to something else that actually does make a bigger change. So give a little bit of thought to these little bits of necessary work. Third thing is duplicated work. So going back to this thing, what this algorithm is really doing is saying, okay, for all AB pairs between 1 and 1,000, generate all the CD pairs and check for matches there. Then go to the next AB pair, generate all the CD pairs over and over again. So we're doing this CD work over and over again. We're constantly generating a list of the CDs and then checking to see if the AB matches any of those values. That work is repeated. So maybe we think, well, let's take this CD loop and let's just generate these lists of all the CD pairs just once. And then for every AB pair, compute a cubed plus b cubed and look for it in this third column here, which actually isn't going to do us any good because now we're just searching a giant table. But what's a better way of finding values in that? Given this high-level thought of creating a table, what's a better way of finding values in that third column? Hash tables. And again, when in doubt, go back to hash tables. Hash tables. So restructure this as a hash table, map from the actual c cubed plus d cubed result to the pair that got us that. And now for every AB pair, just look up the match in that hash table. And that will get us a much more optimal algorithm. So pay attention to the bits of duplicated work. When you see work that's duplicated, it's very, very common that you're going to optimize that out with a hash table. Space-time trade-offs is our second approach. Again, hash tables, that's a key part of this. Like, we joke that hash tables are a key part of problems, but it's true. I think well over half of interview questions do involve hash tables in some way. So have that at the top of your mind as a approach. And then also other data structures like tries, graphs, heaps that people often forget about. And then also think about pre-computation, reorganizing input. That's another common way we use. Okay, third approach, which might be the one I use the most, which I call do-it-yourself, DIY. So given two strings, S and B, S is a smaller string, B is a bigger string, find all permutations of S within B. So I've asked this problem, well, dozens of times at least to people, and then many, many times in these kind of sessions. Pretty much everyone can do this. They'll find a way of doing it, and it's usually generate all the permutations of S first, and then do a substring search on B for each one of those. Which is fine as a brute force. What's the runtime of that? So how many permutations of S are there? By the way, most people don't remember this, but I know some people here do. Yeah, S factorial. Then you have to do a substring search on each one within B. Depends on how our substring string search works, but there are linear time substring search algorithms. So that'll give us a S factorial times B algorithm. I'll see a lot of candidates who will take that and then start looking for a faster way of doing the substring search. And it's like, great, suppose you get that substring search magically down to O of 1. But you still got this S factorial hanging out here, right? And S factorial is like a really big number. Like, factorials make exponential algorithms look fast. Like, if you think about 2 to the n versus n factorial, both are n things multiplied together, but at least for 2 to the n, they're all 2's, right? Factorial is really, really bad. When you have S factorial times B, optimizing B is just irrelevant. I mean, even if S is going to be pretty small, it's still just irrelevant. If S is 14, so just a 14-character word, we're talking about 87 billion permutations. Add in one more character, now we're doing 87 billion things 15 times. That's where like the bottleneck is S factorial. And so we just need to not do this factorial thing at all. So let's go back to what we should have been doing in our second step, which is drawing an example. So here's an example. Here's an S, here's a B. It's pretty generic. It's has, I made a couple things here to be clear, like S is, it's not giant, but at least it's not, 2 characters. It has some duplicate elements in it. It's not all unique characters, which for a permutation problem is a good thing to avoid. For a permutation problem, you want to have some duplicate characters in there, because that's a common error. But okay, here's an S, here's a B, so here's an input. What's our output going to be? What are some of the permutations here? B, A, B, C. B is B, C, D. Okay, that's one. What's another one? Yeah, over here. Over here. Someone else said 9 over there. Yeah, 11, yeah. And so here's our permutations. Pretty much everyone can do this, right? You could throw a 5th grader up on a whiteboard and they could, 5th grader who doesn't code, which is going to be like a minority here, but you can throw them on a whiteboard and they can do this. They can get all the permutations. Not particularly hard. And what's interesting here is people will get completely stuck on this previous thing about generating all the permutations. And they just search for all of them. And I've had many people argue with me in interviews that there is no way to get rid of that factorial, because there's no way you could possibly find all the permutations of S in B without first having generated the S. And they can prove this to me. And yet, right here, we found them without ever generating the permutations S, right? Clearly, there is a better way of doing this. And what pretty much everybody does, if you have them step back and say, okay, but how did you get to that output? It's pretty much something like this. Is this a permutation? Is this a permutation? Is this a permutation? Is this a permutation? Is this a permutation, et cetera? And that's just common sense how people are going to do it. And pretty much everyone does the same thing. And this happens for a ton of problems. There's a ton of problems where doing it, just going through an example, gives you a pretty good algorithm. The other thing people do sometimes is they take the first character of S, which is an A, look for all the A's, and look at the surrounding characters. It's actually more or less the same thing in the end, just a different way of thinking about the problem. But either way, it gives you a pretty good algorithm. So that is one huge way of solving problems. Just come up with a nice big input, something that's big and generic. This is the kind of thing where if you come up with an example of S, which is A and B, it's not going to be nearly as instructive to walk through it. Come up with a nice big example, something that really makes you work. Get that output instinctively. And really try to make it instinctively. Forget about computer science and algorithms. Forget about that this is actually a strategy. Just get to the output. However you naturally do it, just get to it. And then after you've done that, now reverse engineer your thought process and think, what exactly was it that your brain did to get there? And pay attention to some of the little optimizations you made. So most people did something like this. Is this a permutation? Is this a permutation? Is this a permutation? Is this a permutation? Oh, E actually isn't even in that string. They just skip right over it. That's an optimization, and actually a pretty nice one. Particularly it'll be hard to articulate that in a big O kind of way, but in the real world, that's actually a pretty big optimization. And that's something I'd say about 50% of people instinctively do. And it's pretty good. So use those things to your advantage. Use your examples. Those will be really, really helpful if you come up with big examples to help you work through problems. Okay, so the next thing you do after this is not coding. This is where a lot of people go wrong. They come up with their algorithm, they feel pretty good about it, and then they start coding it, and they're not quite good enough in it. And you can see it when they're writing code where they start to slow down, start thinking about things a lot more. Maybe they haven't thought through certain things like their data structures. That's a big problem. When you come up with your algorithm, don't code it yet. Take a few minutes to walk through it and make sure you understand exactly what you're able to do, what you're going to do. You should know how your code is structured, what are the functions you're going to be calling, certainly what the data structures are. I see lots of people code and they literally don't know what kind of list they're using. And if you don't know that, you really don't know what you're coding. Walk through it. If you have indices at all, walk through it with those indices and kind of keeping track of how they're moving and when they're moving. Especially problems that seem kind of easy. A lot of times problems that seem algorithmically easy are actually kind of annoying to actually implement, because then trickiness comes in the updating these indices in particular ways without running into little off by one errors. So take the time to do this. It will save you so much time down the road. And if you get confused as you're walking through, as you're trying to actually code, go back to your example, walk through it again, solidify your thought process. Many candidates will get confused, but they're in the coding portion, and so they'll try to force their way through coding, and it just does not work well. If you get confused, go back to your example, figure out what you're doing, and then come back to your code when you feel confident with it. Don't push through. That's like you're lost, you're driving and you're lost, and so you just keep driving and hope that it'll just work itself out. Yeah, it might, but it'd be a lot faster if you just got directions, right? Same thing here. If you're lost when you're coding, continue to code is actually very unlikely to wind up with the right code accidentally. You're going to have a lot better time figuring out what you're doing. Then come back to coding. Okay. When you code, your goal is to show me that you're a great coder. It's not just, can you throw up some pseudocode of this. Your goal is to show coding skills. I'm assessing that. So that means things like correctness, readability, maintainability, performance. Even if interviewers don't articulate those specific things, those are the things they end up looking for. You want to code beautifully. Not just correct code, but beautiful code. So some simple things. Try to write straight. Nobody's judging your handwriting, really. It's very, very, very unusual that I've been in an interview where someone's writing has actually been an issue at all. But what happens, so don't worry about trying to write neat. It's just, you're not really going to change your handwriting anyway. But what does happen is people have this line creep issue where they write like this or like that. And it ends up, I'll actually be okay. I've seen people code this stuff dozens of times, and I have the luxury of just sitting back and watching and observing what's happening. But what happens is you get confused because now your indentation is all off because there's an angle in your code. Your indentation's all off, and it ends up causing a problem, right? So just try to get your lines straight. You don't have to write pretty writing. Just try to write lines straight. Code in the top left corner, or however top left as you can reach, code up there. A lot of times people will code, it's hard for me to but they'll code down here. I'll start coding up there. Kind of a quarter of the way down the whiteboard. And you just give yourself as much vertical space as you can. And write in the far left. Because you write left to right. Give yourself as much space as you can. If there's stuff you don't need on the whiteboard anymore, erase it. You probably want to keep your example up on the whiteboard. So maybe you would want to start off with writing an example on the right side of the board, but you can always rewrite an example. It's usually pretty easy, but code in the top left corner. Arrows are fine. Don't worry about that. If you run out of space, you need to insert new code. Just use an arrow. It's fine. Shorthand is usually okay, especially in a verbose language like Java. And this is why Java is actually not a big disadvantage in an interview, because although it's verbose, that can be largely compensated for with shorthand. So rather than writing descriptive variable names like number of children, which you should write at first to show good variable names, in subsequent references to it, just abbreviate it as NC, or ask your interviewer, make sure they're okay with it. I see a lot of people just do N and kind of pretend like they just wrote really quickly, N scribble, C scribble. That's fine. If there's a bunch of checks that are basically the same, minus just a different variable name, that's where quotes are useful. Often that happens with recursive problems, where you need to recurse up, down, left, and right, and it's basically the same code. You just need to update the indices, right? Use quotes and just show how the indices would change. Make your life easier. Yeah. Yeah. Yeah, that's fine. Yeah, if your language that supports that, that's fine. Java is insanely verbose. So, hash map string comma integer, my hash map equals new hash map string comma integer. Your interview will end before you can get to that. So, hm s comma I, my hash map equals new hm dot dot dot. That'll be fine for most interviewers. Double check, but most should be fine with that. Think about boundary checks, error cases, things like that. This is where shorthand can often be useful because it's not intellectually interesting code, but it's stuff that your interviewer might still want to see. If the sanity checks are there's a lot of them, you might just push them out to a validate method. Sometimes you can do that and then just explain out loud what you would check in that method, but not write it quite yet, because it's less interesting than everything else. Style matters. Adhere to a style guideline. If you are in a company that does not rigidly enforce style guidelines, you're likely to make these kind of errors. So start enforcing yourself to work according to a coding style guideline. And that means things like variable naming. Spacing is a really big thing, especially if you are coding on a laptop or a computer during the interview. Spacing is one of those areas where you see a lot of sloppiness around. You can space things in different ways, but you need to be consistent with how you do it. And then modularization is really, 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 really important, and a way of just making, not only does it show good style, but also makes your life a lot easier. So this is code for something called the ransom note problem, which is basically, I'm writing a ransom note, and I want to know if I can, so ransom note, I'm cutting letters out of a magazine to make this note. Can I build this note from this magazine? So the way you do it is you basically walk through the note and count how many times each letter appears. You walk through the magazine, count how many times each character appears, and then you compare those. There's actually some more optimizations that are minor from there, but that's basically the thought process. This is not what you want to code. This will take you a very long time, and you probably won't finish the interview before that you write that stuff. What you want to write first is just this. You haven't written these methods yet. You just call them. Build the character frequency table for this, build one for this, compare them. That's the very first thing you write. And from here on out, the rest of the coding is just diving into details here. What is the next most algorithmically interesting piece of this thing? In this case, it happens to be the build char frequency. Fine, write that next. Any little concrete chunks of code, pop that out to another function. So convert a character like A, B, C, D, that's not built into the language, to a number. That's a very concrete piece of code. Pop it out to another function. Don't just write it off the bat. And at some point, you might get down to methods that are just kind of boring. So a method to sum an array. If that's not built into, assuming that's not built into the function, into the language, like if you just have some method that needs to sum an array, like that's not something you need to write. So like this is a problem which is basically, given an array, can you split it into two different sets or arrays that order does not matter? So can you split into two different things with the same sum? Two different lists with the same sum. So the way to approach this is basically sum the array and then figure out if there's a subset of elements in there that sum to half that sum. So I see a lot of people do something like this. So first thing, so they call their method, sums the array. If its sum is odd, return false. Otherwise, walk through this. Right? That's not, you're going to spend the first minute of time doing something that's kind of like summing an array. I mean, not everybody can do this, but if you can't do that, you're certainly not doing the rest of this much more complex stuff. So I learn nothing from having you do that. What I'd rather you do is just call the sum method. Call it and write it at the very end if I want you to, but I'll probably just not have you do it because you've either done okay on the rest, in which case I don't need to see that. You can write some really simple method. Or you haven't, in which case being able to write some really simple method doesn't help that much. So, okay, so those are the coding things. Last thing you have to do in an interview is you have to test your code. A lot of people forget about this. It's just going through the motions of testing is important. So you got to test your code. But there's a strategy to doing this. So first thing, do a conceptual walkthrough of your code. So that means just at a high level, it's basically like explaining your code, like for a code reviewer. Just a high level walkthrough. So not a test case, just walk through how it works. Think about every single line of code. Then double check the high risk lines of code. So a line of code like that, it could have a bug in it, but it's really hard for it to have a bug. Even if it had a bug, it'd be something like, oh, you mixed the order of A and B. Something like this is really hard to actually write correctly. I would say 95% of the time someone has a line of code like that, something's wrong. The -1 should have been in there, or something else was wrong. This is really, really high risk. Any kind of math, even simple like arithmetic and division, That's the kind of stuff that you want to double check because people tend to get that wrong. So double check those kind of things before you even go into test cases. Just double check those things specifically. Then when you do test cases, do small test cases. Big test cases people think will be better, and they're actually ends up being worse for whiteboard coding. Because what happens on a big test case is you run out of time. You don't have time to walk through a big test case generally. And so what happens is you're running short on time. One, you don't even finish it. But secondly, if you do finish it, it's through rushing. And you didn't actually walk through everything that happened. You just made a bunch of assumptions about what your code does. And you never really tested it. So small test cases are better because you can get through them faster and figure out the bugs faster. But also, you end up being a lot more thorough. So do small test cases first, which means that the example that you use to generate an algorithm is usually not a good one to actually test your algorithm against. So use small test cases, then go to some edge cases. Think about edge cases as both boring ones, like nulls and empty, but also interesting ones like permutation problem with all the same character, or with capital and lowercase characters, those kind of interesting test cases. And maybe big test cases if you have time, but you probably don't. Other thing with testing, 2 other points I want to make with this. Make sure you're testing, when you're walking through test cases, make sure you're testing your code and not your algorithm. A lot of people I see testing, and they claim to be testing, and yet they're not looking at their code. So either they have an amazing memory, or they're not actually testing, right? They're validating that their algorithm still works, which hopefully that wasn't an issue in the first place. But they're not actually testing their code because they're not looking at it. You're testing your code means walking through line by line, plugging in every value, and actually doing the math required to get to the output, not just assuming that it gets the output you want. Because if you could make that assumption, then there's really no point in testing anyway, right? So, for example, this little bit of code that converts, counts out how many times an A, B, C, D exists in something. A lot of people look at that and be like, well, I'm going to assume that this is going to give me the right values, and it's going to give me this value. So they just assume it does, and don't catch that there's actually a little bug in there. The other piece is the flip side of this, which is that they plug in everything dutifully, but they don't think about if their answer was actually the right thing. You want to be doing both. You want to plug things in and also think about if that was the right thing. So for example, this is for that permutation problem, where you walk through B in windows of size S, sliding that along. You don't want to fall off the edge of B, so you want to stop a little bit early. So we have this for loop that goes from I equals 0, I less than b.length minus s.length, I plus plus. And what else people do here is they're like, okay, well, they'll get a 0 in there and not think about, or 0 on the second part up here, they'll end early and not think about if that's the right thing. So imagine you plug this in and you say, okay, well, what if you plug in here S equals cat and B equals cat? So this is kind of an interesting edge case. S and B are the same string. What happens when we plug in the same value here? So doesn't one, right? We're doing I less than b.length minus s.length. And that's if they're the same string, then they're going to be the same length. We'll get 0. And so this goes into the third point, which is think before you fix things. So we have this bug. We plugged in our value. We thought about it. And we have a bug. Don't just go fix it. Make sure you know exactly what the bug is. So if we plug in here and we have the same string, we're going to not have our for loop executed at all. And so what a lot of people do is they say, oh, no, I have a special case. When B and S are the same length, I need to do this other thing instead. And yes, that technically fixes it for that problem, but that's not really the bug. The bug is actually that we always end our for loop 1 too early. We actually end off by 1 error. When people fix prematurely, people will fix prematurely based on how to fix it for that one input, and it gets us bad fixes. So what you want to do instead is do b.length minus s.length plus 1. So think through your fixes. Okay, so these are the steps you want to do for testing and fixing things. Again, follow this flow chart really, really thoroughly. Just literally walk through it step by step. But 3 things I wanted people to take away. If you forget everything else, 3 things I want you to make sure you take away into an interview. First thing, create a big input, something nice, big, generic, something that makes you do work. Then, this goes into algorithm generation, walk through that input. Forget about computer science, interviews, algorithms, all this stuff, strategies. Just walk through it and get the output, however you naturally would. And then never, ever code until you're ready. And that means both until you are ready, you really understand exactly what you want to code, and that you understand all the edge cases and this and that. You know exactly what you're coding, but also until your interviewer wants you to code. Make sure that your interviewer actually wants you to code that piece. A lot of times people will be like, how can I possibly have time to get a brute force an optimal algorithm and then an even more optimal one and code all three? You don't. You shouldn't be coding all three. Your interviewer probably doesn't want to do that. They probably just weren't a good enough interviewer to cut you off from coding. So before you start coding, ask your interviewer if they want you to code that thing, because often they don't want you to code something. And that also goes for little functions that are kind of easy, like something just to sum an array and you've written everything else. Just ask your interviewer. Make sure that they want you to code that stuff. It is their interview to drive, but a lot of them aren't very good drivers. So you need to take more ownership yourself. Okay, so quick final thoughts. At a high level, I talked all about the engineering side here, but this is about both being a good engineer and a good teammate. So I didn't talk about it today because I didn't have time, but the behavioral stuff matters. It is important. Not only because you will be specifically assessed on that, but because every interview starts out pretty much always with some behavioral questions, and fairly or unfairly, that biases your interviewer walking into the technical questions. So when you come off as somebody who's really smart and accomplished in the very beginning with behavioral questions, that's going to change how your interviewer perceives everything else. They're more likely to give you the benefit of the doubt, things like that. But also, the other side of being a good teammate is about just how you act. One of the things people will do is, they don't want to hire people who are jerks, who are, who argue excessively about things like that. So people are pretty flexible in terms of a lot of other personality attributes, but that's a deal breaker for most companies. So this behavioral side really does matter, even though I didn't talk about it today. And then last thing I think it's the last thing, wanted to leave you with is just making sure you all know and understand that how you think you're doing is not predictive of performance. And there are actual statistics to back this up. When you walk out of the interview and you think you did really well or you did really poorly, or during the interview, that's not reflective of anything. The reason why you think that is typically either that you moved through the problems quickly, you seem to get good answers, but that's like I give you all a curved test, and you see that you got a 60 out of 100. Is that a good score or bad? Well, if everybody else got a 30, you did great. If everybody else got an 85, right? When you see that you move through the problem quickly, you don't know, or you move through it very slowly, what you're actually doing is you're comparing it to your own performance in the past on different problems. Right? You're like, gosh, that was a hard problem for me to get to answer, and usually I'm so much better than that. I must have done poorly. And it's like, well, that was just a really hard problem, and actually you still did really well. Or you perceive your performance based on how your interviewer acted towards you. But your interviewer is always supposed to be nice. They're always supposed to be happy and charming and supportive, whatever. If they're not acting that way, that's because they don't know how to act that way. It's because, or they're having a bad day or whatever. It's stuff that has nothing to do with your performance. The biggest driver of how your interviewer treats you is just their own attitude. That's kind of true in life in general, right? People treat you certain ways based on who they are, not as much based on who you are. So when your interviewer is saying things, pushing you really hard, it seems like they don't like you, that's them. And I actually saw this when one of my old office mates, when he interviewed for my team, he was like, when he came in and he actually got hired, he was like, I can't believe I got an offer. I thought I did horribly. Especially on so-and-so's interview, he did awfully. I'm like, no, I remember that. I remember that interview. I remember him talking about it. You did amazing. But the person he interviewed with is someone who doesn't come off as super smiley and happy, and he thought this person's upset with him because he's doing poorly, and not at all. That's not at all what was going on. And in fact, a lot of interviewers are just as likely to be nice. Like some interviewers might be nicer when people are doing better, but a lot of interviewers are nicer when people are actually doing worse, because then they kind of feel bad and they feel like you need more support and blah, blah. So you can't read into any of this. Do the best you can, keep working through problems, but your perception of how you're doing does not mean anything. So always keep trying to do your best. Okay, so that's all I have today. I'm happy to stay for questions. I do have books, but I actually sold out of books just before this, so sorry. But if you have books here, I'm happy, or of anything, I'm happy to sign. But I don't have any more for sale, unfortunately. Okay, happy to say actual words for question, but I know it goes into the next session after this as well. And then if you want to hear me talk on the other side on how to hire, flip side of this, I'm talking, I think, back in this room at 5. Thank you.
Change our course with the wind. Found my better me in the small things you see. Discovering a home again. When the day fades away and there's nothing left to say, I'll read your thoughts.